Okay, I've got a Brayton refrigeration cycle here. It's got a compressor pressure ratio of 6. Okay, coming into the compressor, I'm at 20 psi and 460 Rankine. Therefore, I jump up to 120 psi because of the pressure ratio. So through the the warm heat exchanger, I have 120 psi. Through the colder heat exchanger, where the refrigeration is actually occurring. Oops, that's not. It should be 20 psi. Okay, going into the turbine, which is at state 3 here, I'm at 700 degrees Rankine. Okay, so again, this is the compressor, this is the turbine, this is the hot side, this is the cold side. So 4:1 is actually my refrigeration capacity that I'm looking for at 15 tons. However, before I get there, I got to set my states, right? So I clearly know H1, I clearly know H3 because I have those temperatures. This is air because it's a Brayton cycle, so air is our working fluid here. Okay, now going from 1 to 2, it's an ideal, so it's isentropic, so I'm going to use those relative pressures, right? So PR1 will then give me PR2 because I know the pressure ratio, so I also know the relative pressure ratio. Then from PR2, I'm going to look up H2. I'm going to do the exact same thing for state 3 to 4 for that turbine, right? It's an isentropic turbine, so I can use the relative pressure ratio to find essentially state 4. Okay, so let me go look up state 1 and state 3. Now this is air. It is in English units. Okay, so I have 460 degrees. I have an H of 109.9 and a PR of 0.7913. At, what was the other one? 700 degrees, I have an H of 167.56 and a PR of 3.446. Okay, so let me go ahead and jot all of those down. So this is going to be 109.9 and 0.7913, and then over here I have 167.56 and 3.446. Now again, going from state 1 to state 2, I can basically calculate PR2 over PR1, knowing P2 over P1. Okay, again, that pressure ratio is 6. I know PR1, therefore PR2, because this is an isentropic compressor, is just basically 6 times this value, which is 4.7478. Okay, and then I can go use that PR to actually calculate my H value. So PR is, 4.7478. So I'm right in here between 760 and 780. My H value is going to be 183.62. Okay, so that is 183.62. Doing the same thing over here. PR4 over PR3 equals P4 over P3. This time I'm going to divide this number by 6 to calculate PR4. Okay, and that is going to be, let's see here, PR4. I get 0.5743. Okay, just using the relative pressures for the ideal turbine, the isentropic turbine. So 0.5743 is right in here, just above 480. Okay, that gives me an H of what, about 115 or so? 0.57. Oh, I was looking at the wrong 0.57. Up here, about 420. Okay, so I get 100.23. So I'm right up here with the 0.5743. So that's going to be 100.23. Again, notice that the temperature on that guy was right around negative 40 degrees Fahrenheit. Okay, or 420 degrees Rankine. So again, we're dealing with pretty cold temperatures, which is one of the main uses of using a gas cycle. Okay, to get that very cold temperature there. Okay, now, of course, I want to find the total power. Okay, so I need to find my mass flow. Again, I know state 4 to 1. Right? That's Q in. That's my refrigeration capacity. Right? That equals 15 tons. I'll let you guys do the, well, maybe I'll do the, remember that 15 tons, 1 ton equals 200 BTUs per minute. Okay? So I say 1 ton equals 200 BTUs per minute. That's the conversion factor of that. Okay, so I can get that in BTUs per minute. That's going to equal the mass flow rate. Again, this is across 4 to 1 here, that the cold temperature, that's going to be H1 minus H4. That gives me a mass flow rate of 310.24 pounds per minute. Okay? Again, that's knowing the refrigeration capacity as well as my H values. I can find the mass flow rate. Now, to find the work of the cycle, I just take that mass flow rate times the compressor work, which is H2 minus H4. Subtract off the turbine work, which is going, 3 to 4, excuse me, is H3 minus H4. Okay, so this is what the input to the compressor minus any work that the turbine creates that'll help run that, which means the total work of the cycle, the total power input, is 1942.1 BTUs per minute. Okay. Now that I know that, I can easily find my coefficient of performance, which of course is just Q in, which is given. Again, you can do the conversion factor on your own, divided by what I just calculated, which is the work of the cycle. And from that, I get a beta of 1.54. Okay, so as with every problem we're doing, right? Set your states. Here I do that using relative pressures to do that. Okay, once I got my states, find my mass flow, do that knowing the refrigerating capacity. Once I have my mass flow, then I can find the work of the cycle. Once I have the work of the cycle, I can calculate the coefficient of performance, knowing, again, that refrigeration capacity.